Okay, so we're gonna continue on in Module 1A, Part 1. This is the learning plan. And I'm going to pull up the PowerPoint presentation and we're going to fast forward a bit to where we left off. So the last time we were together, we talked about terminology. We started getting, acclimated to drawing kinematic diagrams for mechanisms, those simplified versions of. So I know that we did example 1.1, we did a sketch of this one. And then example 1.2, we did a sketch, and we also created this on AutoCAD where we had also developed a start file that had some things in that would, kind of automate or help us have be efficient when we make our individual kinematic diagrams. So what we're going to do is we're going to head to our next slide here. That's going to be discussing mobility. Now, this is going to be section 1.7 in our book, which starts on page 8. And mobility is a concept that we also call degrees of freedom. And the degrees of freedom is going to be the number of independent inputs, or the number of things that we have to do in order to position all the other links where they're supposed to be for the function of the part. So basically, it's like, how many things do I have to do to get done what I need to get done? Okay. So if we look at the next page here, we can calculate the degrees of freedom. And the degrees of freedom are calculated using Grubler's equation. And the equation is going to be F, which signifies degrees of freedom, is going to be equal to 3 times N. Now, this variable N is going to be the total number of links in our mechanism. So if you recall from the last time we were together, when we drew our kinematic diagram, we numbered each one of the links, and each one of those link numbers was in a circle. So those are what we determine how many of those did we put on our diagram. That's going to be the number of links in the mechanism. Then the next one is going to be minus 2 JP. JP is a primary joint. A primary joint can be one of two things. It can either be a pin or it can be a sliding joint. And if you recall on our diagrams, our joints were labeled with letters. So how many letters did we put on our diagram? And that's going to be the number that we put there. So 2 times the primary joints. The last one is always going to be 0, at least right now. So the last one is a higher order joint, and that is going to be when we have things like cams and gears. For the problems that we're going to do here in Module 1 are going to just be the primary joints. So we can actually shorten this equation to not include the JH, okay? We are going to be addressing cams and gears in the learning plans or the modules that are specific to those. So we're just going to kind of let that alone for a little while, and we will revisit this when we get to cams and gears for our modules. Now, oh, yes. No, it's a minus. I'm sorry. There's a minus sign. So if there would be any higher order joints in there, we would subtract those off. Yeah. But this basically is going to be a minus 0. So we're going to have 3 times N minus 1 minus 2 JP. And that's where we're going to end our equation for the purpose of the examples that we're going to be doing. Now, there are 3 different values that we can get. The first value is going to be 1. 1 means that our mechanism is constrained. Now, if we think back to degrees of freedom are how many things do I have to do in order to precisely position that mechanism where it's intended to go. So when I have 1 as my degrees of freedom, that means I just have to do one thing. Okay. And what that means is it's a very simple mechanism to operate. And that is usually going to be our goal, is that we want to have a nice, if you would, user-friendly mechanism that isn't complicated to operate. So when we have one thing that we do, we call that constrained. When we have 0 degrees of freedom, that means that our mechanism is locked. And what that means is that it's supporting. So something like a frame is actually going to be a locked mechanism. We're going to maybe put some things together. They can be joined with pins, but they're not intended to move like some of the other things that we've been analyzing. So locked is going to be like a frame, or a truss is going to be a locked mechanism. Unconstrained, on the other hand, is where we have something just greater than 1. So if we end up having a degrees of freedom that's equal to 2, 3, 4, what that means is we have to do multiple things in order to get our mechanism to operate the way we need it to. So it becomes more complex. So it's not that unconstrained is wrong, or it's going to be something we try to avoid, but it's not going to be easy, if you would, as it would be to have an F equal to 1, like a constraint. So, so there is going to be a couple that come up in our homework. Actually, one that comes up in our homework that is going to be greater than 1. So, so you'll get to kind of see how that works. So down below is an example of each one of these. So the first one here is a degrees of freedom of F equal to 1. So this is a constrained a mechanism. So if you would rotate or oscillate one of these members, then the other one is going to kind of follow along. The middle one is going to be a locked mechanism. You can see here, if I try to move anything, it's not going to move because of the nature of the way that it's set up here. And then the last one has more than 1 degree of freedom. So in this case, there are 2 connecting rods, if you would, that go down to the slider. And so if we move this, it's going to be kind of unpredictable or unstable. So, so those are examples of each of those 3. So what we're going to do is we are going to continue on with our practice problems, and we're going to add to those this next example, which is example 1-3. And this is just kind of an overview of it, but you'll find the full problem at the top of page 9 in our book. So I'm going to bring this down. And it says here, example 1.3, figure 114 right here shows a toggle clamp. Draw the kinematic diagram using the clamping jaw and the handle as points of interest. So the handle is here and the clamping jaw is down here. Also compute the degrees of freedom. So what I want you to do is I want to start off by giving you a minute or 2 here to sketch the kinematic diagram that we would make for this toggle clamp. And then what we'll do is we'll compare in just a little bit. So go ahead and get out a piece of paper and please sketch your kinematic diagram of the toggle clamp. Get out. Now, if you wanted to, if you get done with your sketch, we are going to be using AutoCAD to also draw this. And that's going to be the part that you're going to be handing in for your practice problem. So if you did want to open up AutoCAD and open up your start file that we had created the last time we were together, we'll be translating this to gets a little bit more practice using AutoCAD as well. So I'll give you a little bit of extra time here, and then we'll start looking at this together. All right, let's take a look at the kinematic diagram. So first and foremost, as we know, when we're creating our kinematic diagram, we need to decide where is the frame? Okay, where are the joints that are not going to move? And as we look at our clamp here, you can see that there are these little L brackets that go on either side. There's holes where we can mount it to something. So that's a pretty good clue that that is going to be something that's not going to move. So you'll notice that there are two pins that are in here. So this pin and this pin are part of that bracket that's not going to move. So that's going to be a frame member for each one of those pins. So what I did, I'm going to go underneath my camera here. So what I did to represent those, I kind of started mine by drawing the two pins. Now we don't have dimensions for the problems that we have here. So as I said last time, we're just going to make things proportional to get the practice of putting them in place. So these are representing each one of the pins that we see here on that toggle clamp. Now, the next thing that we're going to do is I like to work on the side where I'm going to be doing an input, or input has to happen for the output to occur. So to me, the input is going to be our handle and the output is going to be the clamp side over here. So I'm going to start on the right hand frame member, and you're going to notice that there is a link that is going to go from the frame, and then it's going to go into the pin, the second pin on that handle. So to represent that, that's simply going to be a straight line. So I'm going to draw right here. I'm just going to draw a short straight line. And then on each end, I'm going to draw the circle filled in to represent the pin joints that we see there. Okay. Then what I'm going to do is I'm going to draw the handle. Okay. So the handle you're going to know. So I've got this one in place. I've got this pin here. So the handle is going to go all the way out here. We're going to create one of those triangles and then come back down and then connect. This is all one piece. So I'm going to draw my handle going up. And then if I had dimensions, I feel like sometimes that's easier, but we don't. It's okay. And then I'm going to put this back. There we go. This is 1.3, yes. So I just drew my handle here connected to the little piece right there. Now, the next one I'm going to do is I'm going to put my clamp in place. So you'll notice here that it's connected to the handle. It's going to go down to my other frame member, but then this piece is going to be, you know, kind of a larger area. Now, it did say in the problem that we should have a point of interest on the handle and then also in the clamping area here. So we'll identify those with our labels, but what we're probably interested in here, and if you think about being the designer and how this is going to operate, when we put our handle up here, this is also going to go up. When we put the handle down, this is also going to go down. So because this is going to oscillate back and forth, we probably are interested in where is the bottom of the clamp going to be, but then also the top part, because it could interfere with something. So how I'm going to represent this, and the book does it a little bit differently, but again, as the designer, you have more insights on how you feel it's going to go together. So this is just going to be part of my clamp end here. So this is part of it. And then I am going to actually draw this a little bit different than what they have it. Like I said, they just did one triangle, but I'm still simplifying it, but I feel like I want to know what that top looks like too. So I'm going to kind of take this, and my clamp is going to look something like that. Now, if I had dimensions again, I would be able to draw this to scale, but I'm just drawing it proportions wise here. And then that way, when I want to know how that's rotating, I'm rotating the whole thing rather than just focusing on just one portion. If we peek ahead to theirs down below, they just did a triangle. But to me, and again, if I'm designing this, I want to kind of know what's going on up here too. Okay. Now, it looks like I have all the elements in place. So the next thing I'm going to do is I'm going to add my labels. The first labels I need to put on here are the numbers of each one of the links. Now remember, convention. Number 1 is always going to be my frame. Even if we attach to the frame in 4 different places, we don't call those 1 through 4. It's always number 1, okay? Even if it's a different piece, it's always number 1. So I'm going to start with calling out my frame number 1. Then my next link is going to be, I, again, like to start on the side where I've got the input. So since my handle is the input here, I'm going to call this link number 2, which is connected to the frame. Then my handle is going to be number 3. And then that clamp side is going to be number 4. Okay, so that means that I have 4 links in my mechanism. My frame is always considered one of my links. Now I'm going to label my joints. So my primary joints here are anywhere that I have a pin connection. So I've got a pin connection here at the frame. That's going to be my A. B, it's going to be to the handle. C is going to be the other side of the handle. And then D is going to be back to the other side of the frame. Okay. Any questions on what we see here? So notice that I have all of my elements identified and labeled, as well as my joints labeled as well. I'm going to check the chat. Sorry, I usually try to have that out. I'm going to have that over here to see if there's any questions. So if anybody virtually has something, don't hesitate. Okay, so now that we have this done, let's go over to AutoCAD and generate the kinematic diagram over there. When you hand in your practice problems, you do not need to hand in the sketch if you don't want to, but you will need to hand in the AutoCAD version of it. Okay, so let's go over there and get another look at how to generate the kinematic diagrams using AutoCAD. Yes, Chris, you have a question. Yeah. Oh, you know what? I forgot. The problem wanted us to add them, right? So when it says it, or you can add them because as a designer, you're like, I'm concerned about that. Thank you for reminding me. So it did ask us to put in our points of interest. So one is going to be on the handle, and it's probably going to be the end of the handle. So that's going to be an X. And then the other is going to be on the clamping side. So that's going to be Y. Now, if you were interested, like I added the thickness up here, you could also call this a Z. Okay. So if you can have multiple points of interest. There just doesn't have to be 1 or 2. Thank you for reminding me of that. Now we're ready to put this into AutoCAD. So what you want to do is you want to pull up that kinematic start file that we created the last time that we were together, or our first meeting. And now we're going to simply move and copy and add whatever we need to duplicate the kinematic diagram that we just created. So because I need 2 connections back to the frame, I'm gonna kind of move my frame member over a little bit. So I'm gonna do the move command. You can either grab it in your up in your ribbon, or you can do M spacebar, and that just is the shortcut for the move command. And I'm just gonna put this a little bit of a distance. Oops, I moved it. Shoots, I want to copy. So CO, well, up on the ribbon, copy is here. So I'm gonna grab, oops, copy. There we go. And I'm gonna put that there. Okay. So now I've got my frame member position. The next thing I'm going to do is I'm going to add my handle. So I'm going to start with a line. I'm going to shift right mouse button. I'm going to grab the center, and I'm going to turn my ortho off, and it looks like I'm on the notes layer. So I'm going to go to the object line layer, and I'm going to show this kind of going out, something like that. This is going to go up a little bit and then back down, and then center. Now, if I look back at my diagram, I have a pin connection here at the end, and I also have a pin connection at this end. So I'm going to add those 2 pin connections. Oh, wait, I did that wrong. Oh, I'm so sorry. Let me start over. Get rid of those. I missed. I gotta add my number 2. My handle's number 3. So let me start over. So I'm just gonna delete that out of there and we'll get back on track here. Sorry. If you were working on your own, I'm sure you probably caught that and were wondering, what the heck is she doing? And we'll do something like that. Okay. And now I'm going to copy over my joints. So this is going to be to the center and then endpoint and endpoint. Then what I need to do is I need to go from the center of my frame to the center of the end of that handle. And then I'm going to kind of go like this, like that, and then back to where we started. So something like that. Now, if I look back, I believe I have all my links in place drawn correctly. Now I'm going to put my labels where they need to go. So I'm simply going to move each one of these. So I'm going to start with number 1. I'm going to move that to right about there. Then I'm going to move number 2 to here. Number 3 is going to be our handle. And number 4 is going to be that clamping member. Okay. Then I'm going to add my designations for each one of my joints, which are going to be the letters. So I'm going to move A, and that's going to go here. I'm going to move B, and that's going to go there. Move C, there, and I'm going to move D. Now, what we're calling these, as I've said before, it's not really important that you match up the same D and the C and the A and the B that I have, but you want to have all of your joints labeled and you want to have each one of your links labeled, because when we get into performing analysis in terms of velocity acceleration, we're going to be creating our diagrams, but then when we do our calculations, they're going to be on the different elements. So they just have to match up. Okay. So if I have it up on my diagram and I'm calculating it down below, they need to match up. So, so that's what's important. Then I'm going to move my X to the end of my handle and my Y to the end of my clamp. And then I'm going to copy my Y because I need an extra up here. And I'm simply going to double click on that. And that is going to be a Z. Left click. All right. So I think I have all of the labels that I need. So that means that I can get rid of the elements that I don't need. And then I also want to make sure that I label this, because this is going to be the screenshot that I take that shows that I did example 1.3. Okay. So now something really important that I didn't do yet is I want to save this. I usually do that at the very beginning. I want to save this as example 1.3 so that I have it, I can recall it and then it's going to be in its final form. I don't want to save over that kinematic start file because I want to use that for other ones. So make sure that you don't do that on accident. All right, so now what you would do is this would be your screenshot. Everybody, have everybody's attention so you know what you have to hand in. This will be the screenshot that you're going to use and add to your Mod1a practice problems document, okay? And you don't need to do the top ribbon. You just want to grab around the illustration. So I'm going to do my Windows Shift S, and I'm just going to window around just like that. And this is what I'm going to add to that document, okay? So you can screen snip it however it works best for you, okay? All right, any questions on that part of this problem? We're not done with it yet. Okay, So now if we go back, you're going to notice that we drew our kinematic diagram. We did it in AutoCAD. We sketched it and we did it in AutoCAD. We have all of our labels on. Now what we're going to do is we are going to calculate the number of degrees of freedom using that Grubler's equation. Okay. So I'm going to go back underneath the camera here. And I'm just going to continue on down below the sketch that I created. Okay. You're going to be handing in this calculation. Now you can do it one of two ways. You can either put it on a piece of paper, label it example 1.3. We're going to write out the equation. I'll show you exactly how to do that. Or if you wanted to, you could go back to AutoCAD and you could add the text to show me the work that you would do. Either way. And then you can have it in one screenshot as opposed to in two different places. I'll let you determine how you want to do that. Okay. Just make sure that I can easily locate it when you hand in. So how we're going to write this out, for those of you who've had me before, kind of the same format. We always start when we're writing out our work, we're going to show the equation in variable form first. So we're going to show right down below here, F is equal to 3 times n minus 1 minus 2 JP. And I'm going to stop the equation there. If you wanted to add minus JH and put a 0 in there, I don't care, but I'm going to stop it because we don't have any higher order joints in the example that we have. There's only primary. Then what you're going to do is you're going to fill in your variables. So this is going to be 3 times my n is the number of links. So the number of links that I have are 4. Okay, 4 was the last number that I put in here. And it's going to be 4 minus 1 in parentheses. Minus 2 times my primary joints. My primary joints are A, B, C, and D. So anything that I put a letter on, got 4 of those as well. Okay. So when I do the math here, if I take 3 times 4 minus 3, that's going to be 9. And then 2 times 4, that's going to be 8. My F is equal to 1. Okay. And we're going to put a box around our final answer. There are no units for this. It's just really letting us know how many things do we need to do in order to, position this or make this mechanism work. And the answer is I need to do one thing. I need to actuate my handle, right? In order for it to clamp or unclamp on the other end. So if we look here, the only input I have is that. So we do the degrees of freedom as a check to make sure that you have all the labels that you do. Because if I go up here and I look, okay, how many links do I have identified on my diagram? To get the numbers to come out to be 1 at the end, there has to be 4 here for this 4-bar mechanism. Okay. How many primary joints do I have? In my case, I have 4. So my answer comes out to 1, which is what I would expect, or if you're not sure and you calculate it, does it make sense? And it does. Now, if you would end up with a different number here, if you would end up with something like 2, or if you end up with a negative value, you would have to question, do I have all my labels on here correctly? And that's the point of doing it. It's also going to verify how you intend this to function. Okay. So any questions on Grubler's equation? It's quite straightforward, not that big of a deal. Okay. So both parts for this example, the AutoCAD version of the kinematic diagram and the work on Grubler's equation for the mobility determination. Okay. All right. So now we're going to go and see what else we have on our PowerPoint. I think we do another example. Yes, example 1.4. So for some of you, our next example should look familiar. Okay. Might have some experience with this. So on example 1.4, we're going to turn the page. We have a can crusher. Okay. If you had me for the Creo class last term, this kind of looks a lot like it. Okay. So what we're going to be doing is we are going to be doing the very same thing that we did on the last example. We're going to be creating the kinematic diagram, and then we're going to be calculating the mobility. Okay. So first things first, go ahead and create a sketch of what you believe the kinematic diagram is going to look like. So as we look here, here's the handle for the can crusher. Okay. Here's the connecting rod to what would be, if you would, a slider that's going to go down and crush the can. So go ahead and as you look at this mechanism, where's the where's the frame, where, you know, how many elements or links do you have, where are your joints, and then represent those, you know, according to the standard format that we've been practicing. All right, so why don't we start looking at the kinematic diagram for this one? I'm going to zoom out just a little bit. So the first things first, we have to identify where our frame is, or where is the connection point that is not going to be moving. So if we look at this L bracket here, we would expect that that's going to be mounted either on a table or on a wall, and it's not going to move. So you'll notice that the first connection that we have with that handle is going to be at that point right there. So that would be a frame member. Okay, that point is not going to be moving. So I represented it by just drawing our little frame member like that. Okay, now to that, we are going to connect our handle. So as we look here, just going to draw my handle going up and to the left, something like this. Okay, and then there is a pin right about there. All right, now if I leave my handle looking like this, it kind of looks like two separate pieces, right? So I have this pin joint here. What's to say that these aren't two separate things coming together? But I know that it's a handle that is continuous. So what I'm going to do is to show that it's continuous. This is where we add, you know, those little triangle-y looking shapes to give it a little bit of thickness so that we know this is all one that's going to rotate about that center down there. Okay. So that's my handle. Then the next thing that I'm going to add, that's the handle, I'm going to add this little link right here. Okay. So that link is going to go something like this. Okay. And then there's a pin connection on the end of it. And at the end of that pin connection is my slider. This is the portion that's going to go up and down and do the canned crushing, right? So all I'm going to do is a slider is going to be represented by a simple rectangle. So I'm just going to draw a rectangle here. And then to show that it's constrained vertically, I need to add a vertical line on one side or the other, whichever side it seems to make sense. Even if it would be captured on both sides, we only show it by convention on one side. Okay. So this would be my kinematic diagram. Notice that I'm not, even though this frame member is the same as this frame member, we're not connecting them together. We're not drawing the L looking bracket or anything like that. All we're doing is showing how each one of those elements is kind of in space relative to one another, not how they're connected. Okay. So any questions there? All right. Then the next thing we need to do is what? Label each one of the members and the joints. Absolutely. So we're going to start with number one by our frame. And again, I like to go, okay, what's going to be like the first thing that I'm going to do? This is my handle. That's my input. So I'm going to call that number 2. Then connected to the handle is this connecting rod or coupling. It's going to be number 3. And then my slider, which I consider the output, is going to be number 4. Then what? What do I need to do next? Label the joints with letters, exactly. So my first one, I'm going to start at the beginning here. I'm going to call that one A. This one's going to be B, C, and then whether it's top or bottom doesn't really matter, but there's a D that is always going to be between the sliding surface and the actual slider. Okay, it's going to be somehow captured and constrained there. Doesn't mean that we have to know how it's going to happen, but there is a joint there, a sliding joint. And then lastly, I don't know if it said it in the problem specifically, but probably a point of interest for us is going to be out at the end of our handle to kind of see how far that's going to oscillate, if you would. Okay. So now we're ready to put this in AutoCAD, right? So let's go over to AutoCAD. I'm going to save the drawing that I had before, and then I'm going to open up my Kinematics start file. And I'm going to rename that right away. And this is going to be save as, and this is going to be example 1.4. And now I'm going to duplicate what we just sketched. Okay. So I am going to start by moving my frame, something like this. And then I'm also going to move my slider over here, and I'm going to rotate it because it now needs to not be horizontal. It needs to be vertical. Is that vertical? I think it is. Okay. All right. And then now I'm going to change my layer to be on the object line, and I'm going to add each one of the elements that I have here. So I'm going to do the line command, start in the center. Here's my handle. Center. Okay. Then I'm going to copy my joint from the center of that to, and this is going to be nearest on my line here. And that's going to be, I don't know, right about there. Then I'm going to move my slider because I need it to be kind of there-ish. Again, proportional. We don't have dimensions. And I'm going to draw a line. And it's going to go from the center of this joint to the center of the joint on my slider. Okay. And then I'm going to move my labels. So I'm going to move number 1. It's going to be my frame. Move number 2. That's my handle. You could put it in the, no, I'll put it on the outside. 2. I'm going to move number 3 to that coupler or connecting rod. And then number 4 is my slider. Okay. Then I'm going to label my joints. A is going to be the one that's right by the handle in the frame. B is going to be this one. C, I'm going to put at the center. Oh, can I guess I can fit it in there. The center, the connection to my slider. And then D, you can either put it on the top or the bottom. Is going to be at the connection between the slider and that vertical surface. And then my last move is going to be, I'm going to move X to the end of the handle. Okay. So that means I didn't use my Y or my last joint. So I am simply going to erase those and kind of position this, zoom extents, zoom. Okay. Now, the last thing I want to do on this diagram is I am going to add the text to label this example 1.4. There we go. And then I would take my screen snip and I would put it around the outside and then add it to the document that I'm going to be handing in for my practice problems. Okay. So that's the diagram. Any questions on the kinematic diagram for example 1-4? We're not done yet. Yes. Yeah. Oh, absolutely. Yes. And you'll see that actually quite often. You absolutely could. You can put it right there if you wanted to. Absolutely. Mhm. Yeah, totally good. Yep. Anywhere it makes sense and you have enough space for it. Other questions? All right. So now, oh, go ahead, Tanner.
Every time it disappears, the beam joint just disappears.
Oh, I'll have to look at it when we have a break. I'm not sure. I can't think of anything. Oh, yeah, I'm not sure. Now what we need to do is the second part of the problem, which is going to be the mobility, okay? So if you are having difficulties during our break, which we'll take in a little bit, I'll come over and I'll address that. So let's do the mobility equation for 1-4. I'm going to go back underneath my camera here. And I'm just going to add it to the sketch that I created. And again, you can either handwrite this or you can put it on the actual problem that we just did in AutoCAD. But we're going to start by writing out our equation in variable form. So F is equal to 3 times n minus 1 minus 2jp. So if we have everything labeled appropriately and we have the right numbers in our equation, what is the degrees of freedom, or how many degrees of freedom are we expecting to get for this problem? We're expecting 1, right? Because the only thing that we have to do to crush a can is to move that handle. That's one thing. So we're hoping that, that the mobility comes out to 1. So I'm going to go equal to 3 times how many links do I have? 4. Yep, I've got 1, 2, 3, 4. So I'm going to put 4 in the middle there. Minus 1. And then I'm going to do a minus 2 times, how many primary joints do I have? I also have 4, right? Don't forget D. That's one that's forgotten very easily because it doesn't feel like a joint, but it is. It's a sliding joint. So that's going to be, I'm sorry, 4, not 3, 4. Okay. So now I'm going to do my math. 3 times 3 is 9. 9 minus 2 times 4 is 8. So my F is going to be equal to 1. Okay. So this is showing your work for me. So make sure that number 1, you show your equation in variable form for each one of these. Then you're going to put your numbers in place and then you're going to calculate your value. Okay. So any questions about that and what I expect to see? All right. So then that would be your next practice problem done. All right. Let's go back to our PowerPoint and see where we're at. Okay, the next section here, you're going to notice that we're going to skip a little bit in the book. We are going to go to section 110, which is the 4-bar mechanism. So kind of getting a little bit deeper into defining some specific types of mechanisms. So first of all, the 4-bar mechanism is going to be the simplest and it's the most common type of mechanism that we are going to see applied in engineering. So a 4-bar mechanism is going to consist of 4 links. Number 1 is going to be your frame. Number 2 is going to be your input, okay? And sometimes referred to as a crank if it goes all the way around in a full circle. Number 3 is going to be our coupler or connecting rod. You've probably heard me say that a couple times. And then number 4 is going to be our output link, which can be a follower or it can be a rocker. So that's going to be number 4. And this is kind of gets us into like standard numbering for a 4-bar mechanism. So again, number 1 is the frame. Number 2 is going to be your input. Number 3 is going to be the connecting or coupler link. And then number 4 is going to be your output. So there are a couple different types of 4-bar mechanisms, and it really is going to depend on how they're defined by what their action is going to be. So if I go to the top of page 20, I'm going to pull this down. Here are examples of some of the 4-bar mechanisms. So in this case, we've got, in slot A, we've got a double crank. So a crank is when we have our link going around in a full circle. So if our left one is an input, that's going to go around in a full circle. Our output is also going to go around in a full circle. It's just going to be larger because it's a longer link. So that's a double crank because both the input and the output are going around in a full circle. A very popular one is called a crank rocker. This crank rocker is where our crank is going to go around 360 degrees. That's going to be our input. But the output is not going around a full circle. It's actually oscillating back and forth or rocking back and forth. So they call that a crank rocker mechanism. The next one that we see down here, I'm going to point to D. This is also a double crank, but in this case, they call it a change position because the radius of the path that it's going to go around is the same for both of them. So they call it a change position, and it's really the same circle, but just in a different place. The next one is a double rocker. That means that our input is rocking and our output is rocking. Neither one of them is going in a full circle. And then the last one we have here is a triple rocker, right? Now, as we go to our next and actually our last example problem that we're going to be drawing a kinematic diagram for in our specific case here in our practice problems, we're going to look at example 1.9. So example 1.9 is found on actually the problem statements at the bottom of page 20. And the illustration is at the top of the following page. So it says here, we've got a nose wheel assembly. So I'm going to go up here. We've got a nose wheel assembly for a small aircraft is shown. Classify the motion of this 4-bar mechanism based on the configuration of the links. So if we look here, you're going to notice that we have what looks to me like a motor, okay? And we have this would be our input link, connecting rod, and then we've got the output, which is going to be this landing gear that's going to be activated either in or out. So as we look here, we were just looking at double crank, crank rocker, double rocker. Which one of those three do you think this would classify its motion as? So here's our input and here's our output. Any ideas? Double crank, crank rocker, double rocker. Chris, do you have an idea? It would be a double rocker. So what's going to happen is this, even though this is a motor, it's probably not going to go around all the way. So it is going to oscillate back and forth, which is also going to oscillate this back. So it would be a double rocker. Okay, good. Now what we want to do is we want to take this further and we want to draw a kinematic diagram. So I am not, unless anybody needs me to, for your assignment or for the practice problems, you will be doing this in AutoCAD. But just for time's sake, I am going to just do a sketch of this and I'm going to let you guys finish up with the AutoCAD version of what our kinematic diagram is going to look like. So go ahead and make a sketch of what you believe the kinematic diagram would be. So this is going to be our input here. This is a motor. The center of the motor would be a frame member because it's not going to move. And then you'll also notice that another frame member is over here on the left-hand side, which is going to be the top where our wheel is mounted. Okay. So use those two as your frame members and go ahead and sketch what you believe to be the kinematic diagram for this. Now, if you want to peek down below to see what it looks like, if you need a little bit of help, that's okay. But try to do as much as you can by yourself. kinematic diagram that I came up with looks like this, which is very similar to what they have in the solution down below in this example. Something that I did differently, which actually is totally a personal preference, is the way that you draw the frame members. Notice that I put my hatches at the bottom. I tend to just leave them at the bottom, but you'll notice that they tip these up and they put it on the top because it's like hanging down. Again, that's just a little nuance that truly doesn't affect how it's going to function. So either way, that can be on there. So what I need to do here is I need to number each one of my links. So number 1 is going to be my frame. My input is going to be number 2. Now, according to 4-bar mechanism convention, that's going to be exactly the number that we're going to do. So that's our input, our crank is going to be number 2. Our connecting rod is going to be number 3. And our output is going to be number 4. Okay. If we go back in our PowerPoint presentation right here, this is the numbers that we would use then when we identify as a 4-bar mechanism. Then we're going to add the letters for each one of the joints. So I'm going to start back where I have my input as A, B, C, and then D back to the frame. And then lastly, the point of interest is probably going to be the bottom of our wheel. So I'll call that an X. Now you might say, why don't you just draw it as a wheel? Because it's a simple shape. It's just not part of the convention. So you're going to notice that we just represent this here. And it's really just kind of going down to the bottom of where that would be located so that we can identify what our, limitations on space might be. Okay, so once we have our kinematic diagram sketched, you are going to do it in CAD. You're going to submit with it in the CAD version, but then you need to just add your degrees of freedom calculation. So our degrees of freedom are going to be F is equal to 3 times N minus 1 minus 2 JP. We're going to have 3 times 4 minus 1 minus 2 times 4. So we're going to have our 9 minus 8. And always double check it. Don't take it for granted, because if for some reason when you're looking here, if you don't have enough joints or if you don't have enough links or you have too many, your number isn't going to come out, and then it's going to trigger like, is that right? Or do I have something wrong? So this is going to be 1. Okay. So you'll be handing in then your calculation with the CAD version of your kinematic diagram. Any questions on 1.9? Lex? We're not worrying about those for this either. You're right. This one does have dimensions, which is kind of nice, but yeah, we're not going to worry about that. We'll get a lot of practice with dimensions in chapter 4, which is going to be the second half of number 1. Okay. So let's go back to our PowerPoint. The next type of mechanism is called a slider crank mechanism. This is another version of a 4-bar mechanism, and it's going to consist of a frame, 2 links, and a slider. Okay. So in this case, we have, looks to me like a slicer of some sort, and it's going to be actuated by the crank that we see above here. So as this crank goes around, our slicer or our blade is going to go up and down, and it's going to be constrained vertically. So this is going to be what we call a slider crank. We have sliding on the output, and the crank is going to go all the way around. And then the last slide that we have here is really just an overview of the things that you need to know in order to create your kinematic diagram. So first and foremost, the CAD that you use, but then also sketching, whether it's manual or using the CAD. In CAD, you're going to be just using those very basic drafting skills like drawing lines, circles, putting things at endpoints, midpoints, nearest, whatever it might be. Additionally, you're going to be putting some text in place, and you're going to have to be able to dimension at times as well. So kind of like the very, very basics fundamentals of CAD. Our drawings, our layouts, our kinematic diagrams are not going to be used to give to somebody to make something. It is going to be for our eyes only, and it's really the layout work that you do at the start of a design. Okay. So that it looks like we're at the end of the PowerPoint. So that means that our lecture demo is done for chapter 1, which is the first part of module 1. What I'm going to do is I'm going to stop the recording here, and then we're going to look at the elements that you're going to be handing in, specifically the practice problems, and then also our assignment. We'll do an overview of that. So I am going to stop recording at this time.